The next four videos, starting from this one, will focus on orthogonality and approximation. So this one is going to be about orthogonality, orthogonal sets, and orthonormal basis. So let's go ahead and see what this has for us. So talking about orthogonality, orthogonal sets, and orthonormal basis, we try to refresh our minds on the idea of inner products, which we saw, which is also dot products, by the way. We saw that, I think, in one of the opening videos on this playlist about linear algebra. So if you have vectors u made up of u1, u2, all the way to un, and you have vector v made up of v1, v2 up to vn. The dot product is simply u dot v, which is just component by component multiplication of the vectors. So you have u1 times v1 plus u2 times v2 plus u3 times v3 plus all of that all the way down to un times vn. So that's just straightforward. And that is the dot product. Now we need the idea of dot product to talk about orthogonality. So let's go ahead and talk about orthogonal vectors, having understood the idea of inner or dot product. Now, orthogonal vectors, two vectors u and v are orthogonal if u dot v is equal to 0. So if the dot product of two vectors is 0, then you say the vectors are orthogonal, meaning that they are the vectors incline at 90 degrees, right? They meet at right angles. So this means the vectors are perpendicular. That is, they make an angle 90 degrees with themselves. Those are orthogonal vectors. So orthogonal vectors are perpendicular, basically. So very good example. So you want to check the orthogonality of u 1, 2, 3, v 2 minus 1, 0. So all you just need is compute 1 times 2 plus 2 times minus 1 plus 3 times 0. So 1 times 2 is 2. 2 times minus 1 is minus 2. So 2 minus 2 is 0. 3 times 0 is also 0. So everything is 0. So since the dot product is 0, the vectors are orthogonal. So it means the vector 1, 2, 3 and vector 2 minus 1, 0 are orthogonal because their dot product gives 0. Okay, then we go for the geometric interpretation. So for non-zero vectors, I've been taking it that u and v are non-zero. Of course, if one of them is 0, then of course that's automatically 0. But then, even though they are non-zero, the absolute value, the modulus, the norm, the magnitude of u multiplied by the magnitude of v times the cosine of the angle between u and v, you know, u dot v is equal to this, generally speaking. But if u dot v is equal to 0, that simply implies that theta is 90 degrees because cos of 90 is 0. So then we say that, of course, if u dot v is equal to 0, then we say that the modulus of u times modulus of v cos theta is 90 is 0. That means if you divide through by uv, you get cos theta is equals 0. So cos theta is 0, right? That implies that theta itself is 90 because cos of 90 degrees is 0. Okay, so for the their dot product to be 0, it means that the angle between them must be 90 degrees. All right. Then, having talked about orthogonality, right? We've decided when two vectors are orthogonal. Let's talk about orthogonal sets. So we say a set made up of different vectors v1, v2 up to vk. That set is said to be orthogonal if any pair of vectors in that set or in that ortho in that if any pair of vectors in that set is orthogonal, right? So in that case now, if you say v1 dot v2, v1 dot v3, if you pick any two sets and you find the dot product, you always get 0. So in that case, you say that you have an orthogonal set. In that case, of course, I is not equal to j because if you find vi dot vi, you won't get 0 for sure. So in an orthogonal set, every pair of vectors is perpendicular, right? Every pair is perpendicular. So then we talk about the property of orthogonal sets. Every orthogonal set of non-zero vectors is linearly independent. So every orthogonal set of non-zero vectors is linearly independent. So if you have all these vectors and they are all non-zero, so every such set is said to be linearly independent. So and we see that orthogonal sets are always independent. And the idea of independence tells us that, there's no redundancy, basically. That means one vector is not a multiple of the other. So every vector is distinct on its own. All right. So you cannot factor out a vector from another one. So talking about orthogonal sets now, let V1 be 1, 1, 0, V2 is 1 minus 1, 0, and V3 0, 0, 2. Let's see, we want to check if the set, right? If the set containing these three vectors is orthogonal. And what will make that possible is if V1 times V2, V1 times V3, V2 times V3 are all 0. So let's check. So if you compute V1 dot V2, that is dot product, now V1, V2. So if you check V1, V2, 1 times 1, 1, 1 minus 1 minus 1. 1 times minus 1 minus 1. So 0, 0, 0. So that's automatically 1 minus 1. That goes to 0. Then V1, V3. 1 times 0 is 0. 1 times 0 is 0. 0 times 2 is 0. So V1, V3 is also 0. Then let's go for V2, V3. 1 times 0 is 0. Minus 1 times 0 is 0. 0 times 2 is 2. I mean, the 0. So you can see that every pair of vectors you take and find their dot products, they all give you 0. That means that these three sets will form an orthogonal set. So we say all dot product, in this case, all dot product are 0, and then we say that the set containing vectors v1, v2, and v3 is orthogonal. Right. Now we go ahead to talk about the norm of a vector. The norm, or the length of v of a vector, is actually norm v, which is square root of v dot v. So it's more like the square root of the dot product of the vector on itself, right? So how do you compute it? You have v, you let v to be 3 comma 5, right? Then the norm of this vector now is um the square root of this vector on itself. Well, I mean, if I want to demonstrate that better, so you have v equals 3 comma 4, that's the vector. So the norm of v is simply v dot v, and v dot v simply means you have 3 comma 4 dot 3 comma 4. So that means component by component, you have 3 times 3, you have 3 into 3. Okay, that'll be square root of this, by the way. So the norm is the square root of this. So that means 3 by 3 into 4 by 4. Okay, 4 multiplied by 4, that's 9 plus 16. So that means the norm of v is actually the same thing as square root of 25, and that is equal to 5. So the norm of this vector is 5. Norm of the vector 3 comma 4 is actually 5 in that case, and that's exactly what we have right here. So we have that. Then we go for orthonormal sets. So far we've talked about orthogonality, which tells us that which is the fact that the dot product of two vectors gives 0, meaning that those two vectors are perpendicular. And then we talked about orthogonal sets, where any two pairs of vectors in the set are orthogonal, right? Then now we talk about orthonormal sets. So we say that a set is orthonormal. Now the idea of getting knowing how to find norm is very useful when we come to orthonormal sets, actually. That's why that came first. So a set is said to be orthonormal if, number one, the vectors are orthogonal. So if you have two vectors to be orthogonal, then that's the first condition for orthonormality. Then the second condition is that each vector has a norm of 1. All right. So if you have two vectors orthogonal and each vector now has a norm of 1. In that case, we say that the two vectors form an orthonormal set, so that vi dot vj will always give us, so if you find their dot products, you get 1 because each of them is 1, right? So for all I is equals j's, that is, if you operate the set on itself, you get if the sets are the same, right? But if they are different, if the sets are different, they are orthogonal in that case. So operate the vector on itself, you get 1. Operate the vector on another vector, it's orthogonal. In that case, you have orthonormality. So, and then we also talk about the idea of unit vectors because that also plays into it. So for unit vectors, if a unit vector has length 1, that's why it is a unit vector. So the modulus of a unit vector is always 1. So to normalize a vector, all you just need to do is you get so you say v cap is v over the norm of v. So A vector over its norm gives the unit vector. And if you find the magnitude of such a vector, the norm of such a vector, you always get 1. That's the deal there. So how do you normalize this vector now? Let V be 3, 4. So the norm, of course, we found the norm of this before to be 5, because we know that's going to be 3.4, 3, 4.3, 4. That'll be square root of 3.4.3.4, 3.4.3, right? So that means square root of 25, which is 5. So the unit vector will simply be this vector v now all over 5, and that means 3, you have 3 over 5. So it's like you have 1 over 5 into 3 over 3 comma 4. That will be 3 over 5 comma 4 over 5. Then, now how do you convert to orthonormal? To convert an orthogonal set into an orthonormal set, what do you do? First of all, compute the norms. That is why we learned about how to compute norms. Then after computing them, then you divide each vector by its own norm. That's how to convert a vector into an orthonormal set. So look at this now. So imagine this from orthogonal to orthonormal, from orthogonal set to orthonormal set. First of all, these two sets are orthogonal in the sense that, I mean, these two vectors form an orthogonal set in the sense that 1 times 1 is 1, 1 times minus 1 is minus 1. So 1 minus 1 is 0, 0 times 0 is 0. So everything is, so these two sets are orthogonal, established. And the road to orthonormality begins with orthogonality, right? So once we have established that V1 and V2 form an orthogonal set, the next thing we want to do is to make them orthonormal. What do we do for each of the vectors? We find the norm. So to find the norm of this, we just have square root of 1 squared plus 1 squared plus 0 squared. That will be square root of 2. Then same goes here. Square root of 1 squared plus 1 minus 1 all squared plus 0 squared. That's also root 2. So the norm of this vector v1 is root 2. The norm of this vector v2 is root 2 also. So for the normalized vectors now, u1 will be 1 over root 2. So it means you divide 110 by 1 over root 2. Then the normalized vector here will be 1 over root 2 into 1 minus 1 comma minus 1 comma 0. Okay, so these are the normalized vectors now. So you discover that if you find the unit vector of this now, you end up getting if you find the norm of u1 and u2 now, which has been normalized, you're going to get 1 in each case, right? So these two vectors, u1 and u2, now automatically form an orthonormal set. So two orthogonal sets become orthonormal if you divide them by their norm, like that. Okay, so we go for basis. So a basis is a set that spans the space and it's linearly independent. So a basis is a set that spans the space and is linearly independent. I think we talked about basis and dimensions in a previous video. I think I'm not sure, was that video 30 or 26? One of those videos. Okay, and that takes us to the idea of orthonormal basis. An orthonormal basis is a basis that is orthonormal, basically. So it consists of perpendicular vectors, unit length vectors, and spans the space. So these are orthonormal vectors that span the space, basically. So let's see this example. Standard basis for a two-dimensional real number system. So of course we know standard basis here. That will be 1 0, E2 is 0 1. So this is an orthonormal basis of R2 because first of all they are orthogonal. 1 times 0 is 0, 0 times 1 is 0. Add them together, you get 0. So that means E1 and E2 are orthogonal. On the other hand, they are also orthonormal in the sense that if you find the norm of this now, you get 1. If you find the norm of this, you get 1. So these are orthonormal. So this is an orthonormal basis of the two-dimensional real number system, right? Okay, I didn't do this R well. Let me just come back and do this for R2. Okay, just to make sure they look the same. Yeah, done. Okay, so that goes. Now that's for example 6. For example 7, standard basis of R3 will be 1 E1 100, E2 010, E3 001, like that. So you can see any two pairs you pick is orthogonal because 1 times 0, 0, 0 times 1, 0, 0 times 0. So E1 and E2 are orthogonal. Then E1 and E3, 1 times 0, 0, 0 times 0, 0, 0 times 1, 0. They are orthogonal. So each one, E3, 0 times 0, 0, 1 times 0, 0, 0 times 1, 0. So they are also orthogonal. Then beyond that, you also discover that the norm of each one is actually 1. So it means this is an orthonormal basis of R3. Okay, I have the R3 thing happening here too. So I want to change that to have it appear the proper way. Okay, so there goes that. So so these three is an orthonormal basis of the three-dimensional real number system. Then we go on to talk about coordinates in orthonormal basis. So if you have the set of vectors u1 up to un, which is an orthonormal set, then v, so a particular v which is not there now, is not actually v dot ui times ui plus, you keep going like that. So that same v plus un times un, like that. That means v dot un times un outside. So imagine if you need coordinates in orthonormal basis now, see how this works. So let u1, you have a particular u1, which is 1 over root 2, 1 comma 1. So these are orthonormal bases, as you can already see, because that was the kind of thing we did before. U1 is 1 over root 2 into 1 comma 1. U2 is 1 over root 2 into 1 comma minus 1. If you let v be 2 comma 0, okay? So it means you're going to get this first one now, this v dot u1. So you see v dot u1 now, v dot u1, that is this v times this u1. First of all, you can just even do the ones inside. So you have 2 times 1, 2, 0 times 1, 0. So you still have 2 comma 0, and then so that means you have, okay, we're talking about v dot u1, of course, v dot u1. So you have 1 over root 2, 1 over root 2 in each case. So it's more like you have 2 over root 2. Okay, I think I'm doing too much abstraction. So maybe I'll do the first one, and then we can use that idea for the second. So u1 is 1 over root 2 into 1 comma 1, right? u1 u1 is 1 over root 2 in 1 comma 1, and v is 2 comma 0. Of course, this is the same thing as 1 over root 2 into 1 over root 2. Okay, so if we say u1 dot v, that is the same thing as 2 into 1 over root 2 plus 0 into 1 over root 2. Okay, so of course, this now becomes 2 over root 2. This is 0 here. So, and this is 0. That goes. So we can just rationalize. We have 2 over root 2 times root 2 over root 2. So this now becomes 2 root 2. Root 2 times root 2 is root 4, which is 2. So 2 cancels 2. So we see that u1 dot v is equal to root 2. That's how we got that result there, in case you're wondering how that came about. So that's how we got this root 2 here. So same goes for this also, because you also have 2 times 1 over root 2, then 0 times minus 1. So that goes to 0. So you also have root 2. So C1 is v dot u1 equals root 2. C2 is v dot u2 equals root 2. Now, finally, because you're looking for coordinates in orthonormal basis, so after you do the v dot u1, you now multiply by u1 again. Okay? So you then have, so for the first one, you have v dot u1, that's root 2. V dot u2 is root 2. Then finally, v itself, this overall v now can be expressed as root 2 u1, all right, this u1 now multiplies plus root 2 u2. So in this case now, these are then coordinates in orthonormal basis, like that. Then we go for the Gram-Schmidt process. Well, I mean, this is a kind of introduction to it. I think in a previous video somewhere I'd done this Gram-Schmidt. It was a very long and tedious process, but maybe this one gives more clarity. But interestingly, the next video is going to be based totally on the Gram-Schmidt orthogonality. So it's the same thing we are doing here, but this is like a foretaste, if you like. Or if you don't get to see the other video, you can also already understand Gram-Schmidt process from here. So the Gram-Schmidt process converts linearly independent vectors into an orthonormal set, right? So we already understand what linearly independent vectors are. It means vectors you cannot if one no vector is a multiple of the other, right? No vector depends on the other. Then orthonormal sets means they are orthogonal, and then they have a norm of 1 each. So those such vectors in that set, right? So for the Gram-Schmidt algorithm, what do? If you are given two vectors, v1 and v2, so first you name v1, call it u1. And when you call u1 v1, so the first starting point is your first vector v1 can name it u1, and then the next vector u2 that is going to follow in the order of u1 will be u2, and that u2 now will be v2. This v2 you had left there before, minus v2 times u1. All right, so you can already say v2 u1 times u1. So this is like the coordinates in the orthonormal basis, the one at the top, and that is now all over u1 dot u1, like this. So it's so you have v2 dot u1 all over u1 dot u1 multiply by that U1 like that. Okay. And then you normalize and you have E1 equals U over U. Okay. So um so you can normalize this U2 now. So that'll be U2 over the norm of U2 like that. Okay. So let's go for this. Let's do the Gram-Schmidt in uh in two-dimensional real number system. So let V1 be 1, 1, V2 is 1, 0. So step one, just call this V1 now, call it U1. Okay. So V1 and U1 are the same. So U2 now is going to be V2, this V2 here, minus. So from here now, you see this is V2, V2 U1, right? So V2 times U1, all right, into V2 times U1. So you see V2 times U1, 1 times 1, 1, 1 times 0, 0. So at the top here, you have this one. Then, of course, U1 times U1, U1 dot U1, that'll be U1 times self. That's 1 times 1 plus 1 times 1, which is 2. That's why you have 1 over 2. So the one up here is, this one up here is V2 dot U1, and this 2 down here is U1 dot U1, and then that is into the original U1. Okay. So in that case now, you then have 1 comma 0 minus 1 over 2 times 1 1. That's 1 minus half, minus half comma half. So 1 minus half is half, 0 minus half is minus half. All right. Then you go ahead and normalize. So to normalize this now, this is U2. So E1 now is going to be the normalization of this one. So to normalize this now, you just have square roots of so you have, of course, you still have your half outside. So you normalize, right? That'll be square root of what's that normalization again? The original vector, right? That's half into minus half divided by the norm of that vector. So the norm of this vector is half squared plus half squared. All right, that'll be 1 over half squared is 1 over 4 plus 1 over 4. That'll still be half. So square root of half is 1 over root 2 into 1 comma 1. And E2 now is 1 over root 2 into 1 minus 1 comma minus 1. Well, I mean, if you follow this formula, you'll be fine, right? But in case you don't get it this clearly, you can watch out for the Gram-Schmidt video that is coming after this one. So it's exactly the same thing, maybe more elaborate than this, all right? But if you follow the formula, you'll be fine. So in summary, we see that orthogonal vectors, we get, how do you to find orthogonal vectors, find dot product. If dot product is 0, then the vectors are orthogonal. Therefore, orthogonal set. So you have in a set, you have different vectors, no matter how many. All pairs you pick from that set, they are all orthogonal, meaning that the dot product of any pair of vectors in an orthogonal set is orthogonal. Yeah, is orthogonal. That their dot product is always 0. Therefore, orthonormal set now, like I said, orthonormality starts with orthogonality, and then the other part is that each set is now each vector is now a unit vector, and for you to make an orthogonal vector into an orthonormal vector, uh, for you to make an orthogonal set into an orthonormal set, you have to verify if the pairs of vectors are orthogonal. If that happens, then you now normalize each set, then you make them into orthonormal set. Then we have orthonormal basis. That talks about orthonormality and span. All right. Then we have normalization. Normalization simply means you divide a vector by its norm, basically. And then by doing that, you make it into a unit vector. Then you have the Gram-Schmidt, which Gram-Schmidt process makes a vector orthonormal. And interestingly, in the next video, we'll be focusing more on the Gram-Schmidt process, or the Gram-Schmidt algorithm, if you like, or the Gram-Schmidt's orthogonalization. Okay, so some key takeaways so far. Orthogonality means dot product equals 0. Orthogonal sets are independent. Orthonormal sets have unit length. Orthonormal bases simplify coordinates. Gram-Schmidt constructs orthonormal bases, and we're going to see more of that in the next video. So try your hands on these questions as much as possible to see how well you get the gist. So determine whether the vectors are orthogonal. Of course, 2 times 1 is 2, 1 times minus 2 is minus 2, 2 minus 2 0. So U and V are orthogonal. Find the norm of the vector. Of course, that would just be 4 squared plus 3 squared plus 2 squared. That's 4 squared plus minus 3 squared plus 3 squared plus 2 squared. That'll be square root of that, by the way. That'll be square root of 16 plus 9, which is 24 plus 4. That's square root of 16 plus 9. That's 25 plus 4. That'll be root 29. That'll be the norm of this. We're talking about norm, right? Norm. Yeah, norm is not Yeah, I think that's fine. Yeah, square root of 4 squared plus 9, 3 squared plus 2 squared. Yeah. Then normalize the vector. Of course, in this case, now just finding, divide this vector by its norm. That's what that normalization thing is about. So the norm of this thing is going to be square root of 36 plus 64. That's going to be 10. So it means you have 1 over 10 into 6 over 8. That's 3 over 5, comma 4 over 5. That's the normalized vector. Then you have 4. You can do the same for 4. Check whether the set is an orthogonal set. So compute, multiply 1 times 1, 1, 0 times 0, 0, 1 times minus 1, minus 1. So if you do this to 0, right? Go for the first and the last. So 1 times 0, 0, 0 times 2, 0, 1 times 0, 0. Correct. Then for this one, 1 times 0, 0, 0 times 2, 0, minus 1 times 0. So this is an orthogonal set because every pair of sets there is actually the dot product is 0. Okay, I think we did 1 to 4 before, so 4 to 6 now. So check the orthogonal set, convert the orthogonal set into an orthonormal set. First of all, are they okay, it's orthogonal because 2 times 2 is 4, 2 times minus 2 is minus 4, 4 minus 4 is 0 because this is 0 times 0 is 0. So it is orthogonal. So you now find the norm of each set and divide by that norm, and then they'll become an orthonormal set. Show that the vectors, these are linearly independent. For the linear independence, how do we do that again? Well, I mean, one way to do it is you can make them these whole vectors into a matrix and take them into echelon form. If you get any zero row, all right, that means the set are linearly dependent. But if you don't have any zero row in the echelon form, it means they are linearly independent. Okay, so okay, we've done seven. Let's do 7 to 9 now, or even 7 to 10 if possible. Okay, 7 to 10. Okay, that's too much. So let's do 7 to 8 and then 9 to 10 later. Okay, so find the coordinates of v 3 comma 1 with respect to the orthonormal basis. Of course, we already know how to find coordinate. That's like you have u1 times v, I mean u1 dot v dot times u1, then u2 dot v times u1. So you put them together like that. Then you have 8, 9, 10 finally. So apply the Gram-Schmidt process to this. So first of all, you say u1 is equal to v1. Then you now get u2 to be v2 minus all that. So you use the formula. Determine whether the vectors form an orthogonal basis for R3. Of course, you want to check that out as much as possible. Okay, I guess I can also change all this R3 into the proper thing. Of course, not a big deal, but I just like perfectionism somewhat. So that's why I want to do the normal math thing. So if you don't do that, not a problem actually. Yeah, so I guess that be the end of this video. So try your hands on these questions. Let's see how well you get the idea. And you know, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel free to let me know. If you have subscribed already to this channel, I must thank you so much for that. But if you have not subscribed, I wonder what you're waiting for. Go ahead and subscribe, hit the notification bell so you can always get alerted each time a new video is released, right? Having done that, you can also become a member of this channel. That gives you some special privileges, like you getting to see some videos first, and then so sometimes you get to see you see the video alone as a member. Nobody else sees it apart from members, and many other perks you can see when you click on join. You see all of these things. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.